Hello. In these videos, we are going to look at how we can integrate trig integrals that are a product of tangent and secant. So we have that long list of things we can do. And for certain products of tangent and secant, we're going to use very similar strategies to sine and cosine. So the first example we have is tangent to the fifth secant cubed x. And first, when we have an odd tangent, there is a strategy we can use that actually just puts us back into sine and cosine. And that is we can rewrite this integral in terms of sine and cosine. This integral of tangent to the fifth x secant cubed x dx would be the same as the integral of sine to the fifth x over cosine to the fifth x times 1 over cosine cubed x dx. And now we have an integral that has an odd sign where we can use those same sine and cosine strategies. So we can rewrite the integral in sine and cosine when tangent is odd. However, when tangent is odd, and we're multiplying by secant, there is another strategy we can use. And that is that we can pull out a tangent times secant. So pulling out or factoring out a tangent times secant, we get the integral tangent to the fourth secant squared x times tangent x secant x dx. And we factor out this tangent secant to become a du. We want to make a u substitution to have du equal tangent x secant x. That means to get u equals tangent x secant x, we want u to be secant x. So everything else needs to be rewritten in terms of secant. In particular, this tangent to the fourth needs to be written in terms of secant. Tangent to the fourth is the same as tangent squared x squared and tangent squared x by the Pythagorean identities is secant squared x minus 1. As we have the Pythagorean identities that help us, and we have that tangent squared x plus 1 equals secant squared x. So secant squared x minus 1 equals tangent squared x. Now everything's in secant except for this du. So we can apply this u substitution to get the integral to be the integral of u squared minus 1 squared times u squared du. Foiling everything out, this is going to be u to the fourth minus 2u squared minus or plus 1 times u squared du. And that is u to the sixth minus 2u to the fourth plus u squared du. And we can easily integrate that. Becomes u to the seventh over 7 minus 2u to the fifth over 5 plus u cubed over 3 plus c. And now we've taken the antiderivative, we can plug our u back in, which was secant. So we get secant x to the seventh over 7 minus 2 secant x to the fifth over 5 plus secant x cubed over 3 plus c. And there is our antiderivative or our integral of our original integral being tangent to the fifth, x secant cubed x dx. So we have that same strategy of factor out something to become a du and make a u sub problem. But what if we don't have an odd tangent? If we don't have an odd tangent, rewriting in sine and cosine would very likely be unhelpful. And if we factored out a tangent secant, we get tangent cubed, in this case, that cannot be written with a Pythagorean identity. So if we have an odd tangent, we can factor out tangent secant. But if we have an even tangent, the next thing to look for would be an even secant. So if secant is even, we are going to factor out a secant squared x dx. And we want this to become our u, or our du. We ultimately want du to be secant squared x dx. So that would mean we want u to be tangent x. So we need the secant squared, that's not part of the du, to be rewritten as tangent. And using that same Pythagorean identity, that tangent squared x plus 1 equals secant squared x, we can rewrite this integral to be the integral of tangent to the fourth x times tangent squared x plus 1 times secant squared x dx. And now our u sub can be applied to get the integral of u to the fourth times u squared plus 1 du. Multiplying this out gives us the integral of u to the sixth plus u to the fourth du. Easy to integrate. That would be u to the seventh over 7 plus u to the fifth over 5 plus c by the power rule. And now we plug our u sub back in, giving us tangent x to the 7th over 7 plus tangent x to the 5th over 5 plus c. And there is our integral or antiderivative of tangent to the fourth secant to the fourth x. So when tangent is odd, we want to either rewrite as sine and cosine, or we want to factor out a tangent x secant x and use a u sub with u equals secant x. If secant x has an even power, we want to rewrite, we want to factor out a secant squared x and use a u sub with u equals tangent x. That leaves us with one more case. What if tangent is even and secant is odd? What if we have a situation where we can't use either of those two listed strategies? And in this case, we are going to fall back on integration by parts. So this is going to be an integration by parts example. I'm going to rewrite the integral to show what we're going to use as u and what we're going to use as dv. Typically, the question is asked, what is really easy to take the derivative of and would become simpler when we take the derivative? However, in this case, since it's all trig, the better thing to ask is, what is something I know the integral of? And something I do know how to integrate is tangent x secant x. So when we set up the u substitution, where u is going to equal something and dv is going to equal something, dv needs to be the thing we know how to integrate. And we know the integral of tangent x secant x is secant x. So we can easily set up that dv and v, making u everything else. U is going to be our tangent x, making du secant squared x dx. Filling in the integration by parts formula, we multiply u times v. So tangent x secant x minus the integral of v du, which is secant cubed x dx. So now we have this new integral. I'm going to rewrite it all the way out, that we have found that tangent squared x secant x is equal to tangent x secant x minus the integral of secant cubed x dx. Using a Pythagorean identity again, we actually know that secant cubed x is equal to, obviously, secant squared x times secant x. And secant squared x is tangent squared plus 1. Why we're using that, that will rewrite this integral as tangent squared x plus 1 times secant x. And we can actually distribute this tangent squared x plus 1 to the secant x. I'm going to distribute that and rewrite it as two different integrals. We'll have tangent squared x times secant x dx, and we'll also have the integral of 1 times secant x dx. And the reason for doing this is similar to that integration by parts example of e to the x times sine x. We have the same integral we're trying to find showing up on the side of what is this equal to. Treating it like a variable, I can add that over to the other side to get 2 of this integral of tangent squared x secant x dx, missing some dx's here, is equal to tangent x secant x minus the integral of secant x dx. One formula that is given, and it's done with a fancy u sub, is that the integral of secant x dx is the natural log of the absolute value of secant x plus tangent x plus c. So I'm going to use this secant x dx integral is equal to the natural log of the absolute value of secant x plus tangent x. plus c. And now we know 2 of the integral we're trying to find equals tangent x secant x minus natural log of absolute value of secant x plus tangent x plus c. So if we just divide both sides by 2, or multiply by 1/2 is the same as dividing by 2, we get that the antiderivative of tangent squared x secant x is 1/2 times tangent x secant x minus the natural log of the absolute value of secant x plus tangent x. So when we don't have an odd tangent or an even secant, what we can do is use integration by parts to rework into different integral we can find. The integrals for cosecant and cotangent products follow the same patterns for tangent and secant. And for the most part, majority of these integrals are find a u sub we can make. And in the cases when we can't make a u sub, there is another strategy to appropriately reduce the powers and find an antiderivative.